so here is something what I did at Hot Sauce, and it's just another complex performance issue. I have updated the slides a little, so I'm gonna upload the slides as well today later in the evening, right? So a bit of philosophy in general. I mean, this is very, very high level philosophy in a sense, but it's very relevant for computer performance. If anything is slow, you know, like you're not happy how fast your report is running. I mean, it's there are like two reasons or two classes of reasons, or you can break it down in two ways. I mean, your report may be slow because it's doing too many operations, like maybe somebody dropped an index and you're scanning through the whole table. You're reading a billion blocks or a million blocks instead of 20 blocks, right? You're doing too many IOs. Or maybe the index is there, but the buffer cache is polluted with other stuff. There are other users as well. So you're visiting the same amount of blocks or buffers. You're doing the same amount of logical IOs, but since buffer cache is full of all the other kind of stuff today, you are doing way more physical IOs today compared to yesterday. Same query, same data, same execution plan. You just don't get as good caching today, right? So you're doing many more physical reads than yesterday. Or, your query, your indexes are good, blah, blah, blah. Your stats are bad, or bind variable peaking causes an execution plan you loop in a wrong order. So instead of going through a small table first and then looping into the big table via an index 10 times, maybe you do things the wrong way around. You go through the big table first, take some rows from there, and then you loop to the small table that used to be the driving table, but now it's the other way around. You loop through the small table, maybe 20 million times, because whatever filter predicates you have in the new driving table don't filter well enough. They don't filter early enough. So, you're sort of basically that's one way to look at it. Sometimes things go slower because you're just doing too much work. Sometimes you have just more business to run. You have more customers today and you have more operations to do. That's why it takes longer, right? But sometimes it's something at the database level and so on, or just caching. Yesterday 99% of your IOs came from buffer cache. Today only 90% of your IOs come from buffer cache. And that's like a 10-time difference, right? 1% from disk versus 10% from disk. That's 10 times more disk IOs, right? And the second way to look at it is that, hey, maybe nothing changed in the database. The caching is the same, indexes are the same, the plans are the same, the bind variables are the same, the data is the same, everything is the same. You're not trying to do more work at any level. But for some reason, the storage array today is slower. So whatever IOs you did from disk yesterday or read from disk yesterday, you're trying to do exactly the same amount of IO operations today because nothing has changed, right? Except the storage array is 10 times slower because somebody's running an Microsoft Exchange compact operation on the same storage array, which kills everything, right? So well, I've seen that, right? And that's why and in order to understand the full picture of the performance, we need to understand both sides of this equation, right? And that's why we looked into things like Ash, Ash, what is it, the wait event histogram, right? So we looked into how long individual reads and commits took, right? So we looked into like how long they take, but also you need to be aware of how many of these operations you want to do. Because in my case, in this, so the throttling script that affected the bottom part. I just made things IO slower, right? But I still had the same amount of users, the same schemas, and so on, right? I could take my benchmark and ramp it up to 100 users, right? And now we have 100 users trying to do many more comments and waiting more. So I haven't really made my hardware slower, but I just have much more work to do, right? And need to be aware of how many users I have logged in, how active they are, and how many commits, how many executions, how many logins they're doing, right? So, and all of this stuff can and should be measured, right? And that's just some background. So we use Ash, obviously for long-running queries, you use SQL monitoring. I will show you something about SQL trace, when you look into the recursive queries. But that's why you have a snapper, and the snapper shows you not only wait durations and how much somebody waits, but it also tells you how many logical IOs, physical IOs, how many commits, how many log writes somebody does, and so on. So all these metrics are needed, right? And when these built-in tools don't help, then you take the screwdriver and dive into the C function level and see what the Oracle processes really are doing. You very rarely have to go to that level because, especially with Ash and so on, then, you can get so much out of Oracle's built-in instrumentation, right? And that's the advanced Oracle troubleshooting method what I use, and then teach as well at my classes, right? So I've been doing this for like 15 years in this order. Actually, that's for another day, but it actually shows me how I personally grew as well. The moment I realized that was even before Ash existed, but the moment I realized that the database is just a bunch of sessions, and I can measure these weights of sessions individually. You see, I haven't mentioned StatsPack or AWR here. I mean, they're useful in some cases, but they are not the main tools I use. The moment I realized that the database is just a bunch of sessions, and Oracle has allowed measuring individual sessions weights, from VDOR session weight and so on for a long, long time, then that was where I had my first jump to the next level. Oh my God! Now I actually start understanding what's going on. Now I can actually troubleshoot things where only one user complains, or everybody complains, but everybody's blocked by one user, right, or one log writer, whatever. So that was when I jumped to the next level, back in like 2004 or 5 or something, or I don't remember exactly when, but that's when I stopped using StatsPack and stuff like that, if I had the choice, or as a primary tool. And then the next step was when I realized that, hey, every session here has, well, maybe top SQL is not the right way to put it, but every session has $V session performance counters. So I don't really have to see how much somebody's waiting for something. I can also see how many from VDOR says that what performance counters, like how many operations we're doing, how many soft parses, how many hard parses, how many chained row fetches we're doing, and these looking into performance counters often helped us to explain and understand why some weights showed up, or why the CPU usage was so high, right? And then the final jump to the next level was basically when I started diving into the kernel function level when these counters were enough. Were not enough. Like only when I always start from the beginning. I never jump down here, right? And I guess this I had. I guess number 4 would be that this whole story about ash weight change and stuff like that, right? I mean, I wrote this ash weight change script like in 2013 or something, but I sort of followed this logic of following the blocking session and so on. I followed that earlier, but that helped me to visualize basically, the sort of the topology or dependencies or layers of weights, right, in one place, right? So that sometimes you have only one problem process who then causes trouble for 100 sessions. And when you look into here, you might troubleshoot whatever these 100 sessions are doing here, while you really should probably troubleshoot what is this guy doing. Okay. Anyway, so that's just some background. So anyway, so there are more hacking sessions coming, and apparently, I have plenty of material that I already have in form of slides and demos. I don't even have to come up with new stuff. And I still do consulting occasionally for customers when they have something really complex. So then that keeps me entertained as well. Anyway, okay, so let's get started. So I'll probably go through this a bit quicker because I already have done this. We've done the homework as a demo, but this is where the slide comes from. I tried to reproduce it on my small 2-node rack with Oracle 12, but it didn't reproduce properly. So I'm just going to show you what I had. So it was a Exadata environment, and it was, you see from the number of CPUs, you see CPU cores. It's like 300 CPU cores across the cluster. And it was like a data warehouse analytic environment, and then the customer was doing they were creating a lot of temporary tables. Then they did ETL and then even some queries and reporting, they had like temporary summaries and stuff like that. And a lot of parallel CTAs on Exadata. High concurrency, I think eventually they ended up running with parallel 96. But when before I got involved, they were running like parallel 1000 even or something like that, or they had like parallel 500, but they had 1,000 slaves and stuff like that, and it was just too much concurrency for the system that they had. And you see all from the colors here, if the chart gets very colorful, then that sort of indicates that there is a problem, because ideally you just see a few shades of green and then blue, and that's it, right? In a reporting environment, at least. In a commit, I guess, might be another one which shows up in a busy system. But anyway, lots of concurrency, lots of wait events, and they had I guess this is already after we had sort of enforced this, but you see they have a number of parallel queries in a single instance, but then they had like parallel query with 96 slaves spread across 4 instances, right? So many queries were just running, and having this contention. So well, what did we do? Let's drill down. Let's look into ASHTOP. I didn't care about background processes. I just care about normal processes. And we have CPU, which is normal, but we also have cluster wait events. We have buffer busy. So we apparently, GC buffer busy is like a buffer busy wait, but across clusters. So we have across nodes of a cluster. So that we had a bunch of cases where somebody wanted to probably modify the same block across different nodes. So it's like a hot block contention. And many sessions wanted to, well, apparently like 17 sessions on average wanted to modify, probably the same block in different rack nodes. So it had to kind of ping pong back or, go across cache fusion a lot. And we also see some transaction level locks, ITL entries, some resource manager and so on. Anyway, so I took one of these statements just to zoom in into one statement and see what this one statement was doing. You see, I'm saying, hey, whatever the top level SQL ID is, so that instead of looking into a single session or something, I just look into this SQL ID, right? And apparently, I don't know if it was running for 2 days. You see, I'm using dash stop here. So dash uses the DBA hist version of the table. And this is what this query had done over the last 2 days, right? And it's and you see, buffer busy waits, and interestingly, the file number was 1. So that's I know it. Yeah, exactly. I just recalled I forgot what the problem was. You see, file number 1. So you see, I'm showing file info here, or the wait event info. File number 1 is, well, I don't even have to do that, but it's the this is the PDB. So this is a system tablespace, right? So this is the, sometimes, when you use PDBs and you want to list all files in a PDB, then it doesn't show you well, in this case, the system is in this PDB is that. But anyways, I don't want to go to that level. But file number one is system tablespace, and this was way before PDBs were introduced, right? So our CTAS statement, which was just creating a table in a different tablespace, was for some reason waiting a lot of time for buffer busy waits on this system tablespace. So, and there is just some explanation. So, basically, all of these buffer busy waits are different versions of hey, we want to like modify or access this same block on different rack nodes while somebody else is already working on them, right? So, and this is a different level wait. So this is like we already have managed to pin the buffer. We have opened up this block, or we have pinned the buffer in memory. We can access the contents of this block, but we cannot modify this block because all the ITL entries, interested transaction list entries in this block are already used by somebody. Because Oracle allows you to have like multiple different transactions in the same block at the same time. You don't have to commit one transaction first before you can do a transaction on a different row in the same block, right? So that's why you can have multiple ITL entries. But if the block is full, and you cannot automatically create more ITL entries. You already have four ITL entries in the block, and you have 4 transactions in there already not committed, and now you want to create a 5th transaction in that block, modify another row in there. Well, that's what you have to wait for. You're not really waiting for a row level lock, because you're modifying. You want to access a different row, possibly, but you cannot even start a transaction anywhere in this block because all the ITL entries are busy. So the buffer busy waits are sort of like a lower level contention. But once you manage to take the buffer for your use, then this is like a higher level contention if you run out of ITL entries in this block because of all this concurrency. Okay, so, and basically, yeah, so because we had all these global cache wait events, that means that it looks like write contention across rack nodes. And now the next question is this: okay, what block is it? Especially it's in a system tablespace. That why would we contend on a block in system tablespace when we are creating tables in a user tablespace somewhere, right? So the file, block, and class. So when you look into these wait events, some wait events, the parameters 1, 2, 3 are file number, block number, and the block class as well. Okay. So I did this presentation before, you see, before I had this. I mean, I added this later. You see, now if you run ash stop or ash wait change or anything like that, when we see any wait events where the parameter 3 is block class, I automatically translate the block class number to the the name, right? So I'm actually using just, I can get the block class number from with or wait stat, if you're wondering. So anyway, so now life is easier. So that you will, when just like I showed the mode, in which mode the waiter wanted to get this NQ, I have also added some extra stuff that what block, if you know the block class number, then what did it try to access. So this is like a segment header in this case. But you see, these all block classes are actually shown here. Because sometimes you have a contention on a ASSM block and so on, or undo blocks and so on. Okay. Anyway, so but this was before I had this block class translation done automatically. So I just looked into file number and block number, and I see that, hey, yes, all the contention is in this file system tablespace, and these seem to be the different blocks, right? A few different blocks who contribute to this. So And basically what I did here was I took all these numbers. These are block numbers, right? In this file. And then I said, okay, show me, because one way is you go to DBA extents, right? Let me see if I have DBA extents here. Your typical query is that if you know the file number and block number, then you go and query DBA extents and see where it falls, right? However, it's often a long query, and if this block is so hot anyway, if this block is so hot, then then it's probably in buffer cache. So I can query v$bh and just say, hey, show me, all data object IDs from from the buffer cache where the block ID is in here, right? Because if these blocks are so hot, then they are in the buffer cache likely, right? And if that doesn't work, then you go to DBA extents and query that, right? So anyway, so it looks like all of the blocks what we waited for, what are so hot in rack, but belong to data object ID number 8. Okay, because data object ID is the physical object, the segment ID essentially, right? So all blocks belong to a segment with data object ID 8. So I can go to DBA objects and I query by data object ID, right? And interestingly, if I query, okay, show me which objects reside in this particular segment, I see like 3 associated things. How can we have multiple tables in a single segment? Well, the answer is cluster. Data dictionary, Oracle data dictionary was invented a long time ago. I think this comes from Oracle 6. When Oracle was completely rewritten, right? And clusters were a thing then. Nowadays, you don't really use clusters because you will lose the flexibility, and then all the other, index organized tables and so on. They have gotten so good, So I wouldn't build new apps with clusters and stuff. There's legacy structures in them. But anyway, so we have a cluster segment. That's what we found. And within this cluster segment, we have 2 more like logical objects. We have the table, 2 tables, seg$ and used extents. Used extents is not used anymore because now we use LMT, right? Locally managed table spaces use bitmap blocks in the table space itself to keep track of which extents are used and so on. And well, actually, it's maybe I'm confusing myself. So there is also FET, $, free extents. So that's what LMT takes care of now. That it keeps track of which extents or block ranges are free. But used extents, used to be again before LMT table spaces that it kept track of where the extents of a segment were. But that's not needed anymore because now we use extent maps in segment header, and there are special extent map blocks as well. If you're wondering, you see, if you look into block types, there's something called extent map. If your first few hundred extents don't fit into the segment header block, then additional extent map blocks are allocated within your segment. Anyway, so, but anyway, so now we know. So there's a lot of contention against this object. So, for some reason, when I do a lot of create table as select operations, we have contention here. And that actually starts making sense in a way. I don't know why the contention is so bad, but indeed, when you create the table, when you create a new table, right? Well, obviously you create a new segment, right? When you put data in there and so on. So obviously you will need to insert into seg$ when you create new segments. Just like you have to insert into object $, you will have to insert here. So that, we might be getting somewhere. Okay. So, and UAT is not really used anymore. If you count rows, it has 0 rows in there. If you have LMT table spaces everywhere, then so that leaves seg$. We don't really use UAT, so that leaves seg$. So we are probably trying to insert into seg$. Okay. And when is seg dollar modified? That's when you create a new table or you extend the segment. You add more extents because you insert rows, right? Or when you move or drop a segment, obviously, then you have to delete or something like that. And also, parallel direct path loads can create many temporary segments, especially in the older versions. So that's how it worked. That you had parallel 96. Every slave created its own temporary segments. So you actually had 96 temporary segments. You had 96 inserts into seg dollar. And once the CTAS finished, then there was like a merge done. Then there was another update or whatever it was, just to show that, hey, now it's all one segment. Maybe there was a delete as well then, I guess. So that's how it worked, right? So parallel 96 meant 96 inserts. And when you had many queries like that, then you had even more inserts into the same seg dollar, physical cluster object. Okay, but let's gather more evidence. So it looks like that could be a plausible explanation. But well, I said that I usually don't start with AWR, but when I help a customer with a problem, then I definitely ask for an AWR report from that time as well. And maybe even also from the previous week as well, that when the problem was not there, because it helps you to you'll get everything in one package, right? So you'll get the parameter values and what the disk layouts are, or what the files are and table spaces and so on. So you don't have to ping pong so many emails or phone calls, right? And it can help you to get a different view as well. So if I look into here, at the top weights, other than CPU usage, we have the top weights, and top weights are well, the percentage. That should be, I guess I've lost that should be the percentage, right? It's the same rack weights, right? Let's see how many CPUs we have and then so on. Okay, that's one node, I guess. We looked into all nodes, and I guess as I mentioned here, we also wanted to, sometimes these complex problems show up when you have a CPU starvation or swapping, memory shortage, because then you start getting cases where, I don't know, log writer doesn't get onto CPU fast enough. The IO is fine, but log writer doesn't get onto CPU fast enough to do its work, and everybody suffers. Or you have a memory shortage, somebody gets swapped out, some critical background process has half of its pages swapped out, and then it has to read them back. It has to wait, and everybody else suffers, right? And I guess I just validated that from here we had so much idle time, so we don't have a CPU shortage here, right? So you have to be aware of the, a foundation of the house as well, right? If the house is shaking, maybe it's shaking because the earth is shaking or the foundation is shaking, right? All right. So and and this is what I mentioned a bit of time ago, that when you create a table, then under the hood, Oracle runs recursive queries like that. And these recursive queries will not show up in VDollar session, and they will not show up in ASH. So these system generated, data dictionary or dynamic sampling queries do not show up in ASH. There is some history behind it, so it was just too complex to keep track of this system generated, recursive queries and then putting the old SQL ID back and so on. So they just don't show that. So you should, starting from Oracle 11 onwards, even if this takes a long time, you will not see it in ASH. In ASH, you will see the create table statement which caused this, right? But not actually the statement what was run under the hood. And this is where SQL trace is better, because SQL trace traces everything, But ASH kind of shows you only the user queries, right? So application queries, right? But AWR, has a different view, because AWR doesn't use ASH for this section. It uses VDollar SQL, right? VDollar. Well, I'm not going to try to draw it. So it's VDollar SQL, right? And that at least can give you some idea that you see. we've spent so much time. Maybe we just have done so many CTAS operations. Apparently, we have done 4,000 inserts in the last 15 minutes or whatever the time is. And what is telling is this: elapsed time per execution is 22 seconds. That's per execution. Why would it take 22 seconds just to insert one row? This is not an insert select, it's just one row. Why would it take 22 seconds, right? And we kind of already have an idea because Ash told us that there is contention on this seg dollar. So we couldn't modify because of the buffer busy waits and some ITL wait, right? And this is AWR on another node, Theritos, and that's not from AWR. I think this comes from just $SQL. So it's not even AWR. I think it's no, it is AWR. We queried it. On another node, it's 70 times average execution per second, right? And you see, why did it take so long time? For some reason, it does 800 logical IOs for just a single insert, and almost no physical IOs. So, well, I mean, but 800 logical IOs, that shouldn't take 70 seconds. I mean, if it does 70 milliseconds, maybe even that's too much, right? For this quick operation. So, all right, and now and this is like a SQL trace example, right? So, I mean, SQL trace is then, I guess it's like between Ash and AWR in that sense. It's not as powerful as Ash, in the sense that it doesn't have all these 100 attributes that you can query and group by in Ash, but it is much more complete or thorough. That this stuff, what it does trace, it's much more complete and thorough in that detail, right? So these two should be complementary. It's not either or, right? So SQL trace traces everything you do, including recursive queries, like you see from here, right? And it has a full history, full chronological history. It doesn't just sample every second like Ash and whatever you see. It actually traces everything, right? And you see here again, this is a single execution, executed only once, and it hasn't used that much CPU, but most of the time, 75 seconds, it has waited for something, right? Or sorry, 75 minus this, right? So, so it's 74 seconds something it has waited, and then it's only three blocks read via disk, few logical IOs for few consistent reads, but twice more current mode gets. So these are now the current logical IOs. Consistent reads are when you want to, query data, read data selected as of some time when the query started, but this is when you want to modify stuff. Usually this current gets are when you want to modify, right? So, and that's why we have buffer busy waits, likely, because we want to modify, concurrently, okay? So, this actually, again, comes from SQL trace that has the full, so this is now the wait events of a single execution, right? And we've waited for many different things, including the resource manager CPU waits. So that's sort of similar to what Ash already told us, okay? But anyway, so why does a single row insert? We want to insert one row. We don't want to insert 1,000 rows or 100. Just want to insert one row. Why does inserting one row require that many different IO, like a block visits, right? Okay, so from many sources we see that we have rack contention of a hot block, and these hot blocks, we saw a few different block numbers in AshTop, but they all pointed to a cluster where we have seg dollar, right? And then indeed we saw inserts into seg dollar, which took like 70 seconds just to insert a single row, right? So it's not actually my CTAS operation. So this is what the SQL trace now confirmed, right? So that it's an insert operation that waited for all this, had waited for so many seconds for all this wait events, right? So it's not my CTAS or not my user update. It's the recursive query under the hood, the $insert, which contained it that much, right? And when you run SQL trace in your lab, it's okay. I mean, you'll also see these inserts. You run a C-test, you see inserts, but you don't see thousands of waits just to insert one record. Okay. And then this is, when with complex things, I mean, sometimes then you start, well, coming up with hypotheses. I mean, in the sense that you have an idea how Oracle works in general. Like, I don't claim to know everything about everything, and I frequently realize that I'm wrong or somewhat wrong or have forgotten something. But you follow a systematic approach, so you don't sort of believe in how things work without measuring them, or if the measured numbers show you something else, then it looks like it doesn't work like that, or not anymore, right? That's why it's important to measure all these things what I've talked about. Anyway, so my educated guess was that since I saw global cache events, and since we saw ITL transaction events, in RAC, I mean, global cache event is, hey, let's open up this buffer, open up this block so we could do something in it. And transaction layer is that it's one level, on top of it, or in a sense that once we have pinned the buffer, once we have access to this block and nobody else is modifying it, now let's try to actually do something in it, right? And that's when you need the ITL entries and so on. These are like different layers in Oracle kernel, okay? So, and when you look into, so I try to illustrate what's going on, that let's say that this block is full of rows. There is no empty space. There is no PCT free here. It's all full of rows, right? And now we have 4 transactions already in this block. This is a row, and the lock byte points to the ITL number and so on. This actually starts from 0, but anyway, so you have these different layers. That in order to modify a row in this block, you have to allocate an ITL. And in order to allocate, in order to modify anything in this block, even the ITL entry, you have to actually pin the buffer, right? So that's what the cache layer does. Local pin or global, pin. And you need a local pin anyway, but then you may need global pin as well, if the owner of the block is in a remote node and so on. So that's this layer, and there is even like one layer lower that whenever you actually want to pin the buffer, you want to modify anything in VDAR-BH, where the metadata is kept in memory, you need the cache buffer change latch for that, right? So there's actually multiple levels of activities, right? So you must pin and maybe retrieve the buffer from the remote rack node before you can change or even examine it, or even like use it or read it, so what if you pin a buffer? You manage to pin the buffer, you manage to get all the way to here. Now you're done, you've pinned the buffer. And now you finally can look inside the contents. If you haven't pinned, you cannot look inside it, because maybe somebody else owns it and is modifying it, right? And now you finally can look inside it and you see, oops, I don't have any ITL entries. I already have 4 transactions active, not committed in this block by other sessions. And I don't have any extra space. I don't have PCT free space here to create more ITL entries. That's when you end up waiting for this ITL wait event. So that was like my educated guess. I mean, based on the numbers I saw so far, that might be might be what's happening. That might explain why we have so many attempts, so many waits for a single row insert. So basically it's this. Let me see. we take the latches, we take the pins, we manage to finally get the row, get the block from the remote node, from the remote rack node, and we finally can look inside it. So this is one pin. This is maybe like a global cache wait event. And now we look inside the block, but unfortunately we cannot do what we wanted to do in the block. Because we have enough transactions in here already, we cannot continue. So what happens then? We are not going to keep the block pin. What happens is that we go back, we release the pin. So that others who have transactions in here, they could actually kind of finish whatever they wanted to do, right? Maybe they want to do more updates or, commit a bit later or whatever. So what happens here is that we managed to pin the buffer, but then we got stuck. We couldn't complete our transaction. We released the pin. And later on, we came back again, pinned the buffer again, and then looked in it. But unfortunately, all the transaction slots were still busy. Perhaps somebody else had taken one. So we again got stopped. So, and then later on, we came back again, finally managed to pull the buffer, from the remote rack node to ours. That's another global cache wait, and maybe now we got lucky and we finally got an ITL entry for ourselves. So that's like, multiple global cache waits and multiple ITL entry waits, because we sort of, when this happens, when we cannot do things in the transaction layer, we will release the pin. Because if we kept the pin, in exclusive mode, nobody could proceed. I mean, others cannot even come and commit to the transactions if I have this block pinned. So I have to release it and try again later. So, and later on, basically try again until we finally got lucky. Okay. So it's like a loop. We got in a loop until we got lucky. And this is when we went even deeper. So I didn't look into tk-prof, but we actually looked into the raw trace file. We enabled tracing for one of these sessions, and again, this is something that Ash doesn't necessarily give you. Even though you could sample, there is a view called $v session wait history. It's a different thing from Ash, but there is a $v session wait history view. There is a view called $v session wait history. It's not active session history, it's a session wait history. This is not license separated, but this keeps last 10 wait events of any session. Every session has one entry here, right? Last 10 waits of any session. So you could like really quickly sample these and save them somewhere if you don't want to run SQL Trace, but SQL Trace makes more sense here. So anyway, and that sort of proves my hypothesis that this is this insert into seg dollar. And you see, we have a local buffer busy wait, that's over. Then we have a global cache buffer busy release. So this is for rack, right? But this is just to access the local buffer, right? And you see, it's all the same file and same block, right? So there actually may be more levels to this. So that I just explained you that you have I explained like 2 levels here, but it looks like that in order to access a block which is owned or mastered by a remote node, you need to take a global cache pin first, and when that succeeds, then you do the local buffer. Then you actually pin the local buffer in your local memory, And even we have the contention here, and the third layer is you go to the transaction layer. So, and this sort of kind of shows that you see that apparently we want to do a local access for this buffer, right? Well, let's ignore this. So this is just writing to a trace file, or whatever other writing audit files and whatever. So that's so anyway, so we have a bunch of these global cache events, and then we finally apparently, once we have access to this buffer, and you see here it took a whole second. because the other nodes have a lot of contention as well. So it took a while. Well, I guess whoever was accessing it, they were holding it for a while. But and finally, we finally have managed to get access to this buffer itself, and then we tried to kind of start the transaction in this block, but we couldn't because we ended up waiting for this, right? And then apparently we just released the lock. We could add in queue tracing here as well just to get a fuller picture. But the same thing went over and over again, hundreds of times just to insert a single row, right? So we again did a bunch of global cache work just to get access to this buffer. And once we had buffer access, then we ended up waiting at the transaction level, and that just repeated and repeated. Buffer deadlock and stuff like that. So that's what you get when you have very high contention across thousands of or hundreds of sessions across many rack nodes at the same time. Okay. And I think what made it worse, I don't know if I have I think what made it worse, I think I mentioned it somewhere. Sometimes resource manager even kicked in and it put somebody to sleep. I think it put somebody to sleep while they were holding a pin on a buffer. Anyway, so that's a topic for a different day. So this was sort of the proof I needed that, hey, okay, yeah, this is happening, right? A single row insert into a regular table, not even an insert select, did thousands of current mode block gets, right? Did thousands of logical IOs and wanted to modify the buffer, against a single small-ish table, right? And also the object ID, you would see SQL trace prints that out as well. So you see, it has a lot of info, quite a lot of info what Ash would provide it also has, right? What is object number 9? I don't even remember what this was about. We can take, block class, using the script, or, again, like I mentioned, there is the with or wait stat, right? If you see block class number 4, then just do B class, and it just lists what it is, does some basic calculations, and it's a segment header apparently. But I don't know if it. So SQL trace showed object ID 9 and 14. Okay, you see, so the 14 was seg dollar. We already knew that, and 9 is the index on the seg dollar cluster or something like that, right? So obviously, when you have indexes as well, they may also have these blocks may also have contention, right? So we had a buffer deadlock contention on the cluster index or something, right? I use B class. Okay. And actually, yeah, that's a good point as well. That since like in modern days, you create tables with ASSM storage management, right? You have this level 1, 2, 3 bitmaps and stuff like that. Then data dictionary objects are not ASSM managed; they are free list managed, right? So, and when you have a lot of inserts or modifications, inserts, deletes in a free list managed table, then the free list beginning is in the segment header. You actually have to modify. The segment header may become a contention point, right? Okay. Anyway, so what did happen? And I'm almost done then. So we had lots of concurrent, highly parallel CTES statements. Each parallel slave created its own temporary segment. And in spikes, when they ran their batch job, or they had many queries with parallel degree 96 and more. They at some point they had even more. They started at the same time, so they had like hundreds and hundreds and hundreds, if not thousands, of sessions who all wanted to started to create, creating their own temporary segments for parallel slaves for data loading, so they could merge them later. Right, so they had like 4 pretty big rack nodes, and they had spikes of concurrent seg dollar inserts across these rack nodes. But since the seg dollar, the tables in say, the seg dollar table, it doesn't have very many ITL entries. I can actually just do this. So let's go to Oracle Home, RDBMS. Choose. I mean, if any of you remember that, so it's SQL BSQ is still the table apparently where when you create the database. So that well, apparently it's maybe it's changed. Well, I mean, apparently SQL BSQ is the entry point, but let's look into this. Seg dollar. So we create a cluster to contain the seg dollar. So we create a table seg dollar in this cluster, and apparently they don't even set the init trends, So I mean, I'm not recommending you to do that, but I know that under the guidance of Oracle support, in the distant past, people actually created new databases with having init trends, bigger init trends here, because this setting called. I'm not saying please don't. I mean, unlikely you need to do that. There are other modern versions there are ways to around it, but because this is why init trends exists. That if you expect you have tens of concurrent transactions per block, then you could when you create your tables, you could modify, configure them that, I don't know, a bunch of the data, bunch of space was reserved in this block header for the transaction entries. So and you could even do it for data dictionary tables. So but you don't need to do this nowadays. Anyway, so so we had hundreds of sessions trying to insert or update this seg dollar, and we ran out of ITL entries, and this caused, because of the multi-level nature of this problem, it caused sort of a global cache and transaction locking trashing, in the sense that we constantly we pinned the buffer, and then we tried to start the transaction in the block, but we couldn't because of this. And that's why we gave up everything we started. We sort of released the lock, and later on, tried to do the same thing again, because we cannot keep, if we manage to pin the buffer, we cannot keep it pinned for a long time, because others also want to, others cannot even commit the transactions in there if you have this block pinned. If you have the block pinned, others will wait for buffer busy waits, right? Or global cache buffer busy waits. And since I had so much contention concurrency across rack nodes, then a single insert ended up doing so many waits. Okay. And so here's a PowerPoint bug, so ignore that. So it's worth noting that sometimes when you see these resource manager waits, then sometimes that may cause trouble as well. For latches and mutexes, or most mutexes, it should be that, okay, resource manager is not going to put you to sleep if you're holding a latch, right? So you have to really, latches are usually released fast, so you will only go to sleep thanks to resource manager when you have released your latches. So it's smart enough for that. However, for regular locks, and I think also for buffer pins, when you combine it with this, at least in the earlier versions, you could have cases where a buffer pin holder was put to sleep, and everybody else just waited for buffer busy wait. So it's worth noting that, right? And yeah, seg dollar is a sys-owned free list managed index cluster. That's why we saw segment header contention. And also, when you insert something and you search for space, you may end up walking through a lot of blocks, because that was the problem with free lists. That was the problem with free lists, that you might have ended up It's just a linked list, and you started from the beginning of the linked list in the segment header, and maybe you had to walk through a lot of blocks and pin them and examine them to see if you could, access them, and if you could insert something in there, right? And only when you found the block which had enough space in it, then you still might have found that the ITL entries were all occupied. So you basically went back to the beginning. You started from scratch. And Ash doesn't show recursive SQL IDs by data dictionary queries, dynamic sampling, and built-in things like that. It does show recursive queries what your code is doing. I mean, when you run PLSQL, which runs SQL, then of course you'll see that your SQL. But low-level internal SQL IDs don't show up anymore, starting from Oracle 11, because it was too unreliable before that. So I used other columns kind of to find evidence then, right? And of course, when I ran SQL trace, then it actually showed me the full trace of everything that happened under the hood as well, right? Okay, so how do you fix it? Well, number one is like with anything, that if you wait for a lock too much, or when you wait for I/O too much, you're using too much CPU and everything is slow. Well, do it less, right? That's the universal advice. And of course, what you mean. I mean, well, but that's how you think about it. I mean, when you have lock contention or buffer contention, whatever, you don't immediately start thinking which parameter to change, but you start thinking of, okay, how could I reduce contention on this, right? And like, is there a way to sort of not insert and update these entries frequently? So if you have parallel 96, I mean, every single CTAS operation will use 96 inserts, and that gets even worse if it's a partition table. You may get like 1,000 sub partitions in some tables, per day, right? Or for every hour or something. If it's a big database, then how do you do that less, right? So one option, actually, like back in the old days, was like, hey, can you run do you really need parallel 96? Can you run with less nodes? Maybe people have over parallelized things, right? But Oracle obviously has been aware of these problems as well, and it has kind of fixed these problems with code, in the sense that remember how that each parallel slave creates its own temporary segment. So this is like a legacy thing, which like starting from Oracle 12 and partially in 11, it actually has gone away. So so there is something called high watermark brokering. So there is inserts, high watermark brokering, and this is starting from Oracle 12, I think. So these are all true by default now. So that actually means that Oracle now is smart enough that it's basically the query coordinator, or basically you will allocate only one segment for your parallel query, not 96 segments. You only allocate one segment. You only have one insert. And it's the query coordinator or some memory structure, I'm not exactly sure, who then spreads block ranges from that segment across parallel slaves of the same CTAS statement, right? So and more about that a little later. So because I'm over time, I'll publish the slides, and actually an older version is already in SlideShare, but there is some history about that, and also Oracle guys have written good articles about how it's changed now, so that basically that helps a lot. If instead of 96 inserts per CTAS statement, you will only have one, right? You have like 100 times less concurrency in that sense, right? So and in this case, this problem was, this problem is in modern database versions, it's solved by high watermark brokering. Let me see if I have I have some old, examples what I ran. You see nowadays in Oracle 12 onwards, you have load as select, and high water mark shows up. So it's like, this is the smart load as select. So that knows how to do this brokering. But this, we were on Oracle 11, and it's supposedly fixed there as well. But I'll skip this. You can read it yourself. So this showed up in Oracle 11. So that's great. We use some NQ and so on for kind of managing space. So basically we allocate one large chunk for the CTAS statement, and then spread the content block ranges in there to slaves internally, right? So that's what brokering means. But there was one problem. That's the reality. I mean, in theory it worked, but in practice, it worked for inserts only. Okay, insert appends, right? And for CTAS and alter table move, for some reason, it didn't work. And when we tested, it actually worked in some cases when the target table was partitioned. But if the target table itself was just a single non-partitioned table, then the old-fashioned way of every slave so every slave taking their own chunk, that kicked in, right? And then we actually found that there is a fixed control. I mean, yes, the parameters had changed. That the parameter was true, that high watermark brokering was used for CTAS as well. However, this fix was disabled for some reason. So it worked for insert appends, but for CTAS and the alter table move, this fix was fixed. Oracle had fixed it for a long time ago, but for some reason it was disabled. So you see, I'm showing how many moving parts there are. You see, and this is Oracle. Well, that's Oracle 12, right? You see, there is a fix. If you go to session fix control, there is a fix. Actually, this one, right? That use high watermark brokering for inserting into single segment, even for CTAS and alter table move. It is currently at its default value, but the default value is 0, so it's actually disabled. So the bug fix was fixed a long time ago. The bug was fixed a long time ago, but it was not enabled by default for some reason. I don't know what reason. Maybe it was a bit too buggy, unreliable at first, or whatever. So we had to set this as well, and then finally we got this high watermark brokering. And Alex Fatkulin, or the late Alex Fatkulin, has he was the one who spotted that, and we worked together on this issue with the Enkitech folks. All right, so you see, this was a low-level enough issue that like SQL tuning necessarily didn't fix that, right? I mean, running with less parallelism, and perhaps that would have helped, potentially, but maybe the whole thing would have been slower because we used less resources. But perhaps not running all the 20 queries at the same time, but then scheduling them like with in a staggered way, like 5 seconds apart, would have probably helped as well. Because then instead of having like 2,000 slaves trying to insert to the same table at the same time, we would have had only 96 at a time. And then 5 seconds, 10 seconds later, you run it again. You run the next query because they were all long-running queries anyway. So you'll start seeing how you do it less, after you have measured and see where the time is spent, and then you can have these ideas, right? But luckily, in the modern days, Oracle has all these new parameters that I mentioned. So if you're on Oracle 12, you shouldn't probably worry about it at all because of that. And but in Oracle 11, let me just look into the fix. This is Oracle 18. You see this in Oracle 18, this particular fix is still disabled by default. However, it's probably less of an issue because you have this whole new feature which does some sort of hybrid temp segment merge load method. So I think this new method overrides any of the previous things. So, all right. But Oracle is complex, right? And you have so many moving parts which may affect things, right? So even though you should not see this particular problem again in the future, then who knows what other layers cause trouble in the future, and you need to know how to navigate through them. Okay, and as you see, we're probably out of time, so I'll just skip. So this I've explained this in my blog entry quite many times. You see buffer busy waits as a top weight. So this was a parallel CTAS as well, actually, and you see, and this was a block class 13, the block number 2 in a data file, but class was 13. So if I look into that, it was actually a file header block, but this is not the actual file header. It's not block number 1. It's block number 2. This is the LMT bitmap file space header. That's the entry point into the LMT data structure for space management in a file, right? And if you have a big file table space, you only have one file per table space. So everybody who allocates extents in this big file, they all will contend for the same block because they want to modify bits there. They want to modify bits and see where the next bitmap block is in the file and so on. So, and here's another example maybe to finish is you see hash rate change shows you that as well. We had a lot of buffer busy waits on the file header block, and now you see what were the holders of this buffer bin doing then, right? And when I saw that cell smart file creation and ASM file metadata operations and so on, then this was like an indication that hey, we were not extending. We were constantly having to extend the big file, and when you had hundreds of sessions all wanting to allocate space in this big file, but it was still being extended, or regularly extended while the workload was going on, then we ended up waiting, And I guess the extension was fairly slow for some reason for our data volumes. So, one solution there would have been to pre-extend the data file, like in the old days during a quieter time, or use bigger extent size. So that the root cause, part of the root cause in this case was we were not using. When you have big table spaces where you load a lot of data with big extents, you need to use large uniform extents in there. You should not use auto allocate, because even if you use large uniform extents, like 8 megabytes or 64 megabytes, whatever, as an extent size, if you have an auto allocate table space, then you still have 1 bit per 64 kilobytes, because the extent size is not uniform. It can be varying. It can be small or big in the same file. That's why you have a 64 megabyte extent in such a table space would require 1,000 bits to be flipped. So that will make things slower. So if you have a big table space, you also have to configure it with large uniform extents, because then every time you extend the data file and allocate space within this extended data file, you can get and release this LMT bitmap block much faster, because you have much less bits to flip, and then much less. The LMT structure is much more compact. I'll stop here because I have a whole blog entry about this, right? So it was also interesting. Again, buffer busy wait showed up as a top-level symptom, but under the hood, we started seeing data file extension. And but I still asked the question that if we have so much contention of this, who is holding this lock for so long? I mean, why are we trying to get this? Why are we trying to pin this block so much? And why whoever is holding it pinned, why are they pinning it so much? And why are they holding it pinned so much? And how can I do it less? Because that's how you resolve contention. You do it less. You use it less, right? You either spread the contention. If you cannot use it less, then you have to spread the contention. So my way for doing it less was I used bigger uniform extent sizes. So I didn't have this 64 kilobyte small chunks anymore. I had like 64 megabyte big chunks, and allocating this was way faster. So I used it less. I did it less. Or the other way, if you cannot do it less, you spread the contention. Well, instead of using one big file table space, you're going to use a regular table space with 100 small files. Because when you have 100 small files in it, then every small file has its own LNT bitmap. You can spread the contention. But in my mind, it's always worth looking into doing it less first. That means before you kill the problem with more hardware or spreading the contention, can you somehow reduce the contention? Can you use it less, right? And you think about that, right? And depending on what numbers and what symptoms you see, then there are different ways to do it less, right? All right. Yeah, I'm well within my 3 hour. This is another 1.5 hour hacking session, which ended up taking 3 hours. So, um, well, I'm sure you were not surprised. So I'm taking it fairly easy as well. That's why I call them hacking sessions. Um, it's worth saying that if you want a bit more systematic and then more structured learning, then I actually am going to start my advanced Oracle troubleshooting class in like 1.5 weeks, right? And the SQL tuning will come in June, and I'm going to do my Linux one and later in the year. And I have now videos of all the previous classes as well. But when you sign up, then you can get the videos of the previous class immediately to prepare, so that when we do the live class, live online class, then you can ask better questions or more questions, or you already have some idea of what's coming. So stay tuned. But I'm gonna do more hacking sessions as well. As I said, I'm actually gonna probably even publish like a event calendar for a whole half year, so you can plan for that. And I'm gonna have more fun, and not only in the Oracle space, but also in Linux and application space. So it's gonna be cool. All right. So am I gonna have the complete 3 hour video on YouTube? Yes, because you see, if you go to videos, you click on videos here, then that's my YouTube channel. Or maybe if you go to connect, this is where I have all my, Twitter. If you want, like, to stay up to date, then follow me in Twitter. That's the fastest way. GitHub here, slides, blah blah blah. Slides will be in the slides here. But if you go to videos, go to YouTube. So you see the state object stuff. 3 hours, right? It was 1.5 hour session. It took 3 hours, right? And some of them I'm splitting into smaller pieces, but you see, you have hours and hours of hacking session fun there, right? If you don't know about X dollar traces, how multi-level wait events work, how wait event names can change while you're waiting, look into this 2 hour session and so on. So there is a lot of cool stuff. I should probably replay some of these things myself. Okay. All right. Thanks very much, and have fun, and see you soon.